Black holes are not empty spaces carved into the cosmos. They are not holes in the ordinary sense, nor voids waiting to be filled. They are regions where space-time itself has collapsed inward under the weight of extreme gravity, places where the rules that govern the universe bend, twist, and eventually break. A black hole is a distortion of reality so deep that nothing, not even light, can escape once it crosses the event horizon. They do not swallow everything around them. Instead, they reshape the fabric of existence, pulling matter, energy, and even time into their gravitational well. For decades, black holes lived mostly in the realm of theory, elegant mathematical predictions born from Einstein's equations. They were thought to be possible, maybe even likely, but unproven. Then, in the last few years, everything changed. We have now seen the shadow of a black hole, captured the glowing ring of superheated matter swirling around the event horizon, and detected the gravitational waves produced when two black holes collide and merge. What was once speculation has become undeniable reality. Black holes are the ultimate test of our understanding of physics. At their center lies the singularity, a point where density becomes infinite and our laws of nature collapse. They are cosmic paradoxes, invisible yet visible through the light they distort, silent yet roaring with energy as matter falls inward, small in appearance yet capable of influencing entire galaxies. As we explore the strange truths behind these dark giants, we will uncover 12 things most people do not know about black holes, facts that challenge intuition, reveal hidden processes, and expose the boundaries of science itself. This is not just a journey into astrophysics. It is a descent into the deepest mysteries of the universe, where space curves, time stretches, and reality becomes unfamiliar. Black holes are not merely astronomical objects. They are the places where our understanding fails, and where wonder begins. One of the most persistent myths about black holes is that they behave like cosmic vacuum cleaners, sucking in everything around them with unstoppable force. In reality, black holes do not pull matter the way a vacuum does. Their gravity works just like the gravity of any other massive object, only stronger when you get close. If our sun were suddenly replaced by a black hole of equal mass, Earth would not be swallowed or dragged inward. It would simply continue orbiting, almost exactly as it does now, circling a dark point instead of a glowing star. The reason is simple. Gravity depends on mass, not on appearance. A black hole acts like any other object of the same mass as long as you remain outside its event horizon. From a safe distance, you would feel no difference. Planets, stars, dust, and gas can orbit black holes in stable, predictable paths. Entire solar systems could theoretically exist around them. The only danger lies in approaching too close, where the gravitational field becomes steep and tidal forces grow extreme. This misunderstanding comes from dramatic imagery, swirling disks, collapsing stars, light stretching into oblivion. But those visuals show material that has already ventured near the event horizon, where gravity becomes irresistible. Objects that stay far away are not doomed. They follow the same laws of orbital mechanics that govern everything else in the universe. Does a black hole eat matter? Yes, but only what crosses the boundary of no return. Everything else remains untouched, circling safely in the cosmic dark. The truth is far more elegant than the myth. Black holes don't consume the universe. They simply reshape the space around them. One of the most misunderstood aspects of a black hole is the event horizon. Many people imagine it as a physical surface, a kind of cosmic membrane that objects crash into. In truth, the event horizon is not a surface at all. It is a boundary in space-time, a point at which the flow of time behaves differently for different observers. From the outside, an object falling toward a black hole appears to slow down. The closer it gets to the event horizon, the more distorted its motion becomes. Light takes longer and longer to escape from its position, until eventually, it seems to freeze in place, suspended in a ghostly red glow. To an external observer, the falling object never actually crosses the horizon. It fades, stretches, dims, and then disappears. But this is only an illusion created by the extreme warping of space-time. For the object itself, whether it's a spacecraft, a particle, or a photon, time continues normally. It crosses the event horizon without noticing anything unusual. No wall, no impact, no sudden change. The fabric of space simply curves inward, and the object follows that curve. Inside, time flows forward exactly as it always has. The difference is that all paths now lead inward, deeper toward the singularity. There is no direction left that goes out. This is why physicists describe the event horizon not as a thing, but as a moment, the moment when escape becomes physically impossible. It is a border shaped entirely by gravity, created by the bending of time itself. What we see from outside and what an object experiences inside are two parts of the same reality, governed by relativity. But they could not feel more different. The event horizon is not a surface blocking the way. It is a boundary where time and space trade places, and where the universe stops behaving in ways we can easily picture. One of the strangest regions around a black hole is the photon sphere, a place where gravity is so intense, so finely balanced, that even light itself can orbit. Unlike planets, which follow stable paths, the orbits of light are incredibly fragile. A photon that enters the photon sphere is pulled into a circular path, whipping around the black hole at the speed of light, tracing a perfect ring of brightness. But this orbit is unstable. A tiny push, the smallest deviation, can send the photon spiraling inward toward the event horizon or flinging outward into space. Many photons don't complete a full circle. Some loop a few times, bending dramatically, before either escaping or being captured forever. Others plunge inward, contributing to the black hole's growing shadow. This is the region responsible for the glowing ring seen in the first black hole image ever captured, the place where light is whipped around the hole multiple times, creating a halo of distorted brilliance. It is not a physical surface, but a gravitational trap for light, a circular orbit carved out of space-time itself. Inside the photon sphere, the warping of space is extreme. Directions lose meaning. The idea of straight or forward becomes distorted. A beam of light that would normally travel in a straight line is forced into a curved path, as if space were shaped into a bowl around the black hole. To an observer unlucky enough to fall into this region, the sky would twist into impossible shapes, with stars appearing to smear, shift, or multiply as their light wraps around the hole. The photon sphere is the boundary between the visible universe and the darkness beneath. It is the last place where light can still dance before being lost forever, a ring of fire around a gravitational abyss. The word spaghettification may sound like something invented for science fiction, but it describes one of the most brutal and unavoidable deaths in the universe. When an object, or a person, falls toward a black hole, the difference in gravitational pull between their feet and their head can become enormous. This is called tidal force, and near a small black hole, it becomes extreme long before you reach the event horizon. As you approach, gravity pulls much harder on the part of your body closer to the black hole. Your feet fall faster than your head. Your body stretches violently, first lengthening, then thinning, then tearing apart at the molecular level. Your bones and tissues elongate into a thin strand, a literal spaghetti of matter, before being shredded into atoms, and then into elementary particles. For stellar mass black holes, this happens well outside the event horizon. Death would be almost instantaneous. But near a supermassive black hole, the experience is completely different. Because the black hole is so large, the tidal gradient, the difference between gravity at your feet and your head, is surprisingly gentle at the horizon. You could fall through the event horizon without noticing anything unusual. No sudden stretching, no tearing sensation. You would drift calmly across the boundary, unaware that your fate is sealed. Only deeper inside, as you approach the singularity, would the tidal forces rise to catastrophic levels. There, spaghettification becomes inevitable. Space narrows into a single direction, pulling everything into a thin, falling line of matter. Time speeds you forward, leaving no possibility of escape. Outside, the universe sees you fade, stretch, and freeze near the horizon. Inside, you fall silently into a gravitational abyss. Spaghettification is not a metaphor, it is physics. A universe where gravity can tear apart atoms is a universe both terrifying and profoundly beautiful in its power. For a long time, scientists believed that black holes were eternal, perfect prisons from which nothing, not even information, could escape. But in the 1970s, Stephen Hawking discovered something extraordinary. Black holes can slowly evaporate. Not through explosions, not through cosmic collisions, but through a subtle quantum effect happening right at the edge of the event horizon. According to quantum mechanics, empty space is never truly empty. It seethes with pairs of virtual particles that constantly appear and disappear. Usually, these pairs annihilate instantly, leaving no trace. But near the event horizon of a black hole, the extreme curvature of space-time can pull the pair apart. One particle falls inward. The other escapes outward. To a distant observer, that escaping particle looks like radiation being emitted from the black hole itself. This process is known as Hawking radiation, and it means something astonishing. Black holes lose mass over time. The smaller the black hole, the faster it evaporates. A supermassive black hole at a galaxy's center evaporates so slowly that its lifetime exceeds the age of the universe. But a tiny black hole, one with the mass of a mountain, could evaporate violently, ending its life in a final burst of gamma rays. The idea that black holes can fade away challenges our understanding of permanence in the cosmos. Hawking radiation reveals a profound truth. Black holes are not absolute. They are dynamic objects shaped by both gravity and quantum mechanics. They gain mass when they consume matter and lose mass through evaporation. Their lifespan is not infinite but governed by the laws of physics at their most fundamental level. In the end, even the darkest objects in the universe cannot escape time. Most people imagine black holes as a single kind of object, a dense, collapsed star pulling everything into darkness. But in reality, black holes come in several forms, each with its own origin, scale, and mystery. They range from the remnants of dying stars to ancient objects that might predate the galaxies themselves. The most familiar type is the stellar mass black hole. These form when massive stars exhaust their nuclear fuel and collapse under their own weight. They typically contain a few times the mass of the Sun and fill regions barely larger than a city. These are the black holes we find scattered throughout the Milky Way, formed from generations of dying stars. Far larger and far stranger are supermassive black holes, giants millions or even billions of times more massive than the Sun. They sit at the centers of galaxies, including our own, shaping the evolution of entire star systems. Their origins remain one of astronomy's greatest mysteries. How can something so enormous form so quickly in a young universe? Did they grow by swallowing stars? Did they merge from many smaller black holes? Or did they emerge from exotic early universe processes? Between these extremes lie the elusive intermediate mass black holes, with masses from hundreds to hundreds of thousands of suns. For decades, they were only theoretical, too large to form from single stars, too small to dominate galaxies. Recently, hints of their existence have begun to appear in gravitational wave detections and star cluster observations, suggesting that intermediate black holes may hide in the shadows of dense cosmic environments. And then there are the most mysterious of all, primordial black holes, hypothetical relics from the first moments after the Big Bang. These would not be formed from stars, but from extreme density fluctuations in the early universe. They could range from microscopic to asteroid size to planetary mass. If they exist, they might explain dark matter, or they might be the key to understanding the universe's earliest structure. The truth is that black holes are not a single phenomenon but a family of objects, each revealing a different piece of the cosmic story. From stellar corpses to galactic engines to ancient relics of creation, black holes come in forms as diverse as the universe they Supermassive black holes are among the most voracious objects in the universe, and they grow far faster than intuition suggests. These titans, weighing millions or even billions of times the mass of the Sun, sit in the hearts of galaxies and feed on everything within reach. Drifting gas clouds, wandering stars, entire star clusters, and even other black holes. Their growth is not slow or gentle. It is explosive, dynamic, and sometimes violent enough to reshape the galaxies around them. When gas and dust fall toward a supermassive black hole, they don't plunge straight in. Instead, they form a swirling accretion disk, a spiraling torrent of matter heated by friction to millions of degrees. This disk can become so bright, so energetic, that it outshines the entire galaxy in which it lives. Quasars, the brightest beacons in the universe, are powered by these blazing disks, glowing with the force of trillions of stars. This feeding process allows supermassive black holes to grow astonishingly fast. In the early universe, just a few 100 million years after the Big Bang, some black holes already reached 1 billion solar masses, a mystery scientists still struggle to fully explain. How did they become so massive so quickly? They may have consumed enormous amounts of gas, undergone runaway growth, or merged repeatedly with other black holes in chaotic cosmic environments. But accretion isn't their only method. When galaxies collide, Their central black holes spiral together and merge in immense bursts of gravitational waves, creating a new, larger black hole ready to feed again. Over billions of years, this cycle of collisions and consumption transforms modest galactic cores into gravitational giants capable of shaping the evolution of entire galaxies. Supermassive black holes are not passive monsters waiting to be fed. They are engines of cosmic growth, expanding through ferocious appetite and violent mergers, blazing so brightly at times that they illuminate the universe itself. When a star drifts too close to a black hole, something extraordinary and terrifying occurs. The star enters a region where the difference in gravitational pull between its near side and far side becomes overwhelming. These forces are called tidal forces, and they grow so extreme that the star can no longer hold itself together. What happens next is one of the most dramatic events in the universe, a tidal disruption event, or TDE. As the star approaches the black hole, it begins to stretch. Its spherical shape elongates, becoming distorted, pulled into a long, thin arc. Within moments, the tidal forces shred the star entirely, unraveling it into a glowing ribbon of plasma. This spiraling stream forms a luminous loop around the black hole, twisting like molten light. Part of that stellar material escapes outward, while the rest is drawn inward toward the event horizon. The falling material then forms a brilliant accretion disk, heating to millions of degrees as it spirals inward. Sometimes, the disk becomes so energetic that the black hole launches relativistic jets, narrow beams of radiation and plasma that shoot out from the poles at speeds incredibly close to the speed of light. These jets can travel across thousands of light-years, lighting up space like cosmic lighthouses. We have observed several of these events from Earth. They appear as sudden, intense flares, a star's final moment broadcast across the universe. In those flashes, a single black hole can briefly outshine the galaxy around it. The violence, the beauty, and the sheer power of a TDE make it one of the most astonishing transformations in the cosmos. A star that spent millions or billions of years shining peacefully can be destroyed in minutes. What remains is a glowing spiral, a final breath of light, consumed by darkness. If black holes are the ultimate traps of the universe, regions where matter can enter but never escape, then their theoretical counterparts, white holes, are the exact opposite. A white hole would be a region of space-time where matter can only come out, but nothing can ever go in. It would be a cosmic fountain instead of a cosmic prison, a place where time and gravity flow in reverse compared to a black hole. White holes emerge naturally from the mathematics of general relativity. If you take the equations that describe a black hole and reverse the direction of time, a white hole appears as the mirror solution. But while black holes have strong observational evidence, shadows, gravitational waves, accretion disks, white holes remain purely hypothetical. They have never been observed. If they exist, they would be some of the rarest and most difficult objects to detect. The concept becomes even more intriguing when paired with quantum physics. Some theorists propose that when a black hole finishes evaporating through Hawking radiation, it might not simply fade into nothing. Instead, in the final instant of its existence, it could transform into a white hole, releasing all the information and matter it once contained in a sudden burst. In this scenario, a white hole would be the final exhale of a dying black hole, a brief, explosive moment where the universe gives back what was once taken. Others suggest that white holes could have formed in the early universe, emerging from primordial fluctuations just after the Big Bang. These would be tiny, short-lived objects, scattering matter outward before vanishing as quickly as they appeared. Some versions of the theory even propose that our entire universe could be the inside of a gigantic white hole, a place where matter is continuously expanding outward from an initial cosmic boundary. If white holes do exist, they would be some of the most exotic objects imaginable, glowing eruptions of matter, ejecting energy and particles without ever allowing anything to fall inward. They would defy our everyday experience of gravity and time, standing as reminders that the universe may be guided by principles we do not yet fully understand. White holes remain a mystery, not proven, not disproven, but they open a window into a universe stranger and more complex than anything we have confirmed so far. For more than a century, physicists have wondered whether black holes could do more than collapse matter, whether they might also connect distant parts of the universe. Out of Einstein's equations emerged a strange and beautiful possibility: wormholes, tunnels through space-time that could, in theory, act as cosmic portals. If black holes curve space downward into a gravitational well, a wormhole would be the bridge that connects that well to another location, perhaps millions of light years away, or even a different universe entirely. Mathematically, a wormhole looks like two mouths joined by a thin passageway called the throat. One mouth could resemble a black hole, where matter enters. The other would act like the reverse, something similar to a white hole, where matter exits. This kind of shortcut through space-time could allow travel faster than light without breaking the laws of relativity, because the traveler wouldn't move faster than light locally. Space itself would be folded. But there is a problem. Wormholes are unstable. If you tried to fly into one, the throat would collapse instantly, crushing anything inside. Gravity would snap the tunnel shut before a single photon could pass through. To keep a wormhole open, you would need something exotic, a form of matter with negative energy, capable of pushing space apart and stabilizing the tunnel walls. Negative energy is allowed by quantum mechanics, but only in extremely tiny amounts and fleeting durations. No known natural object generates enough to support a traversable wormhole. Still, the idea refuses to fade. Quantum theory, string theory, and modern gravitational physics all leave room for wormholes as mathematical possibilities. Some physicists even suggest that microscopic wormholes may form and vanish at the quantum level all the time, tiny tunnels flickering in the vacuum of space. Do black holes lead somewhere? Could they be entrances to hidden parts of reality? We don't know, but the equations whisper that the universe might be stitched together in ways we can barely imagine. Wormholes remind us that the cosmos is far stranger and far more flexible than our everyday experience suggests. Falling into a black hole is one of the most mind-bending experiences physics can describe, not because of what you feel, but because two completely different realities unfold at the same time. One is seen by a distant observer. The other is experienced by the falling object itself. Both are true. Both contradict each other. And both exist because space-time bends differently for each participant. Imagine you are drifting toward a black hole. From your perspective, the journey feels normal at first. You accelerate smoothly. Stars behind you begin to distort. The glow from the accretion disk brightens. As you approach the event horizon, the boundary beyond which nothing escapes, you see nothing special. No wall, no barrier, no flash of light. You simply cross it. Time flows forward for you exactly as always. Inside, space funnels inward, guiding you toward the singularity. Gravity grows stronger, but the descent feels continuous, inevitable, and strangely silent. But to an observer watching from far away, something completely different happens. As you approach the event horizon, your motion slows. Your signals become stretched and redshifted. Light from your body grows fainter and more distorted. It looks as though you are moving through thick, invisible syrup, slowing, dimming, freezing. You never appear to cross the event horizon at all. Instead, you fade into a dim, red smear, frozen in time at the edge of darkness, until your image slowly disappears. Both perspectives are correct. The event horizon marks a boundary in time, not space. For the outside observer, time at the horizon appears to stop. For you, time continues uninterrupted. This is the magic of relativity. Two realities, equally valid, born from the curvature of space-time itself. What you feel, and what others see, are two different stories, separated by gravity, connected by physics, and united in a single truth. A black hole bends not just space, but experience. Black holes hide their greatest secrets behind a boundary no light can cross. Once something passes the event horizon, all information about it is sealed away forever, at least according to classical physics. This leads to one of the deepest scientific enigmas ever discovered, the information paradox. If information truly disappears inside a black hole, then quantum mechanics, which insists that information can never be destroyed, must be wrong. If information doesn't disappear, then our understanding of gravity and space-time must break down. Either way, something fundamental is missing. General relativity tells us that space-time curves inward until it forms a singularity, a point of infinite density where our equations fail. Quantum mechanics, on the other hand, insists that space-time cannot collapse to such extremes without preserving the data encoded in every particle. These two pillars of modern physics, usually in perfect harmony, collide violently inside a black hole. We cannot look inside to find the answer. We cannot send a probe. We cannot shine a light. No telescope will ever capture an image beyond the event horizon. Everything that happens inside is cut off from the rest of the universe. A perfect cosmic curtain. Some theories propose that information is stored on the event horizon itself, encoded like a hologram on its surface. Others imagine that black holes leak information slowly through Hawking radiation, bit by bit, over unimaginable time. Some researchers speculate about firewalls, fuzzballs, or quantum bridges that connect universes. Each theory tries to reconcile the rules we know with the mysteries we cannot test. But the truth remains unknown. The inside of a black hole is the ultimate blind spot of science, a place where our understanding collapses, where the mathematics breaks, where the universe whispers secrets we cannot hear. This is not just a mystery. It is the greatest puzzle in 21st century physics, the frontier where quantum mechanics and relativity meet, clash, and demand a deeper theory yet to be born. Black holes remind us that the universe is bigger than our knowledge, stranger than our equations, and more mysterious than anything we can imagine. And some doors, once crossed, never open again. In the end, black holes are not monuments to destruction. They are gateways to deeper questions. They sit at the edge of our understanding, not as dead ends, but as beginnings. Whenever we look at them, we aren't just staring into cosmic darkness. We are confronting the limits of the laws we build to make sense of the universe. These objects take everything we believe to be fundamental, space, time, matter, information, and bend them into shapes we can barely describe. They remind us that the universe is not obliged to be simple. It is not required to fit within the boundaries of our textbooks. In the shadow of a black hole, general relativity falters, quantum mechanics stutters, and even the concept of causality begins to unravel. And yet, instead of closing the door on knowledge, black holes open 1,000 others. Their very existence is a challenge, a quiet, gravitational riddle demanding a new theory that unites the largest scales with the smallest, the cosmic with the quantum. Maybe somewhere inside these hidden regions lies the key to a deeper framework of physics, a theory that doesn't break at the singularity, doesn't lose information, doesn't contradict itself. A theory that will show us that what we call impossible is simply not yet understood. And so the final thought lingers. As we gaze into the shadows of black holes, they gaze back, not as monsters, but as mirrors. They reveal the true darkness, not in the fabric of the cosmos, but in the gaps of our knowledge. They remind us that mystery is not an obstacle but an invitation, that the more the universe hides, the more it urges us to look deeper. And the greatest discoveries may not come from what we can see, but from what refuses to be seen at all.